So now I will introduce again Daniel Tosaus from the University of Zaragoza to take us through the OpenAI clip model leveraging the RTVE content. Daniel?
Right. I'm Daniel, and I'm going to present to you a proof of concept that I've been working on as part of the RTVE University of Zaragoza chair. And it is regarding whether or not we can use some state-of-the-art AI models to automate the segmentation and description of TV programs. In this particular series of tests, we're going to be using a model called CLIP. This is a multimodal neural network, which means that it can work with text and images. It has been designed and developed by OpenAI, and it has been trained with 400 million pairs of image plus text. This means that this model, this AI, has learned to identify the semantic concepts within a given image or text. So with this kind of technology, we are trying to ask ourselves, can CLIP be used to segment and describe TV programs? To explain a little further and understand how this model works, I have a little example here. We could use as input of this neural network any given image or text, and the CLIP model will return a semantic vector. This vector would contain the semantic concepts within those images or text coded into 512 values. As I've said, we could do the same thing with text, and these semantic vectors that we are computing using this AI, this CLIP, would be in the same semantic vector space, which means that we could compare the semantic concepts in that space and find similarities between them. To better visualize this concept, we can use these semantic vectors and reduce those dimensions, those 512 dimensions, into just 3 for visualization purposes. In this case, we can very easily see that the images that contain the same semantic concepts than the texts are closer in this vector space. So this could mean that we can perform searches based on the semantic information that is within an image or within a text. So we're going to go through some tests that we have performed in search applications with using text as the input and also using images as the input. If we use this phrase, this text as input, we can observe this kind of results. To do this kind of search, what we did was compute those semantic vectors for the frames of a number of RTVE programs. So we formed a database of those semantic vectors. With that database, we can input this text, compute the semantic vector of this text, and then compare and find those semantic vectors or those frames that are more similar to the semantic concept represented by this phrase. In this case, we can see that the general results are good, but we can find some of the results as errors. And this can be explained by the way that this model understands the semantic concepts in this phrase. It is searching for frames that contain the semantic object of a man, but also the semantic concept of eating, and it is finding relations with food, as we can see on this table, or even the relation that can exist between this basket and the food. This behavior where the model is trying to find similarity with a lot of semantic concepts that are within the input, it's stronger when we use an image as the input. In this case, we were using this image of this man eating a burger, but the model will return as very similar some frames that contain a man with a shirt, just like the input, something that it is related with the food, and even it seems to have understand the burger as a unique semantic concept, and it has related it to the lettuce. And in this particular case, we see that the general whiteness of the input picture is showing great similarity with other very bright frames. So when we see this behavior, we can think maybe using image as input for this type of search is not very useful, but there is a particular use case when this could be very practical. And this is when we need to find the program associated with a given frame. In this example, we see that we are using as input of the system a picture that contains a frame, but this frame is rotated and even cropped. And although it may seem that it's a lot of semantical information, the model is capable of returning the specific program that contains this frame, and even find other semantical concepts or semantic concepts like the glasses of wine, and make that relation with some other program. And what happens if we step back and take a picture from far ahead? In this case, we're showing the model that there is even more semantic information in this picture. We are showing that there is a PC screen, and there's a keyboard and a mouse, and there is some kind of desk. When we do this, the semantic information that is within this tiny frame goes to a second plane, and the system finds more similar frames that contains computers, screens, and desks. I think this is a good example to see how this model understands these semantical concepts and how it can be used to find content in a given database. So now I'm going to talk about how or whether or not this technology could be used to perform automatic TV program segmentation. And the fact is that the semantic information in a TV program, in the image of the TV program, varies all the time. And if we could compute those semantic vectors of all the frames in a program, we could see, like in this representation in 2D, that the concepts are moving around, and the frames that contain similar semantic concepts will appear next to each other in this kind of vector space. With this in mind, we can try and look for some patterns in the TV programs, and use those patterns to find segmentation marks. In the case of our tests, we are doing our experiment in RTVE's program Aquí la Tierra, which have a fixed structure in which every time that the program wants to introduce a new topic or a new subject of the program, the shot will change to the TV set with the TV presenter. This means that if we can describe with natural language text, for example, these kind of frames where the presenter is in the TV set, we could know when in the progress of the program are the segments with the TV set. So we could use that information to know where or when a given segment of the program starts and ends. So following this strategy, this approach, we tested a lot of text inputs, but finally we stayed with this one indoor TV presenter in front of a screen. And now in this representation, what we are seeing is the similarity that has every frame of the program with the given input. with a given input. So when the similarity is very high, we know that we are probably in the TV set, and where it's very low, we are probably in an outdoor environment. So doing this, we could establish a threshold, and with this threshold, we can implement a detector. This detector could allow us to know where or when the TV set show up in the program, and give us that segmentation marks, those segmentation points that we could use to know where or when a part of the program starts or ends. Just for comparison purposes, I have added here the marks that were manually added to this program, and even when they don't match exactly, it gives a general sense of a good performance, because we see that a lot of the segments have been found, and the fact that the marks are not in the exact same moment are mainly because the default criteria to determine where the segment starts is not the same with the two methods. So we could think that maybe some of these marks were skipped by this automatic algorithm, and that's true. One of the cases would be a shot of the TV set like this. In this case, the model clip wouldn't know that he's looking at a presenter in a TV set, so he would be fooled, and this would be skipped, resulting in a missed segment. So now, considering that we have a preliminary segmentation of a TV program, we would like to know if it's possible to use this same image information with clip to describe those video segments. How we're going to do this, or how can we try to do this? Well, we can try to compute those semantic vectors beginning with an image, and then try to go back across clip, but not into an image, but into a text, keeping those semantic elements. To achieve this, it is necessary to use some natural language synthesizer like GPT-2. We, in our test, have used this publication right here, and this is a real example of a description that could be generated in this manner. We can see that when the photo shows a simple semantic concept and there is not a lot going on, the description can be very accurate. So the approach that we took to try and describe a video segment was the following. We would take the frames that belong to a given segment and generate a caption of each frame with this method. Then we would treat this set of description as text and obtain a summary of this text using another model, an abstractive summary. In this way, we would try to obtain a description that takes a little bit of every moment in the video segment. Now I'm going to show some of the preliminary results doing this. We have to point out that this GPT, this clip model, has been trained with a lot of images, but not with, it has not been fine-tuned with data that we could then use, not with RTVE data. So in this particular example, we're seeing that the model can understand some of the semantic concepts of the video segment, but it can fail and output some grammatic errors or orthographic errors. This is mainly because this is a preliminary test, and we are putting some model after another with barely any adaptation, and when the descriptions are not of good quality, the final summary can have these errors. But we can see that the general sense of the meaning of the segment, it is stated here. If we see another example, in this case, we see what would be the normal behavior of these video descriptors. It is very curious and is worth mentioning that in this case, because CLIP was trained with so many images and descriptions, it can happen that you try to describe an image that contains information that was on the training dataset of CLIP. And in this case, it knows that this is a Spanish actor. And when you try to describe the frame, it states the occupation of the person as part of the description. This is a very easy proof of the power that can have this tool. Then we have this example when we can see the potential of these descriptions, because it is a very detailed description. It even says and describes how are they slicing the meat with a knife, and this seems like this model can describe with this quality almost every segment, but that is not true, because as we can see in this other example, the system is often confused with screens, especially with screens that are showing natural images, like this one. It would mix the image of the beach with the presenter. But when the images projected on the screens are not natural, the model usually describes correctly. So now I'm gonna go over a simple future line of work that we are currently in, and that is facial recognition and tracking. The idea behind this is to avoid this segmentation mark skipping that we have mentioned before. And in this new approach, we would search for the face of the presenter. We would crop it and then try and find the same face in all the other frames in the program. So we would know if the presenter appears in a scene. And if he does, we will know that we are in a TV set, and we could use that timestamp to segment the video. To wrap it up with some final conclusions of these experiments and tests, we must say that CLIP and the fact that it is multimodal represents a step ahead from the previous models. That we have observed a great preliminary results in TV program segmentation, and it can be even improved with other approaches. And regarding image and video description, that we have seen some promising results, and there's plenty of room for improvement, because as I previously said, we have just taken some models and put it one behind of the other. And lastly, I've stated here that these descriptions, video descriptions, are always in English. So it is required to develop advanced and multimodal language models to achieve these accurate descriptions in other languages. So thank you for your time.